I'd like to continue where I left off, trying to read Einstein on the electrodynamics of moving bodies. I was in the midst of section 3, the theory of the transformation of coordinates and times from a stationary system to another system in uniform motion of translation relatively to the former. And this is at the bottom of page 8. We had just derived a formula rating del tau del x prime and del tau del t. When we have partial derivatives with these little del symbols, it means that something is being held constant while the variable in the denominator is changed. So whenever you see a partial derivative, there is an actual unstated assumption about something else being held constant. Sometimes actually you do see the assumption made explicit, and I did this at the end of the last video, stating that del tau del x prime with t held constant plus v over c squared minus v squared del tau del t with x prime held constant. And this is the same thing as holding x equals vt. All of that equals 0. Now for a moment I'm going to skip over this paragraph and go to the one that starts, since tau is a linear function, it follows from these equations that tau equals a times quantity t minus v over c squared minus v squared times x prime. Now I wish I had the expertise in differential equations to know what exactly he means by linear function and exactly what axiom to look up in a textbook. But lacking the book knowledge, I'll attempt to justify this statement with a bit of basic reasoning. What I'll imagine then is a space-time diagram and two events in the space-time, and then I'll set up a couple of isoclines in x prime through those two events. This could be x prime equals x prime sub naught, and then this will be, let's call this initial, and this one will be x prime final. At those two events, there should be a clock reading, and the clock reading at the initial event will be tau sub initial, and the clock reading at the final event will be tau final. We'll also create a third clock reading right here. Let's call it tau b for tau between. And it is the clock reading that happens at x prime final simultaneous with tau initial at x prime initial. So now let's define tau initial, or tau between minus tau initial as delta tau 1, and tau final minus tau between is delta tau 2. In going between tau sub b or between tau sub initial and tau sub b, only x prime changes, and tau changes at a constant rate del tau del x prime over that change in x prime. And in going between tau sub between and tau final, x equals vt plus a constant. I may have said that wrong earlier, but x prime does not change. So delta tau 2 here is partial tau partial t delta t. So if I add these two things together, I'll have delta tau equals del tau del t delta t plus del tau del x prime delta x prime. Now this expression up here gives us the relationship between partial tau partial x prime and partial tau partial x, partial tau partial t, and partial tau partial x prime. So let's get that in there. Del tau del x prime is going to be minus v over c squared minus v squared times delta tau delta t times delta x prime. Then let's just factor out the delta tau delta t. We'll have delta tau delta t times delta t minus v over c squared minus v squared delta x prime is equal to delta tau. So this equation is identical to the one Einstein got, except where he has quantities measured from x prime equals 0, the origin of k, tau equals 0, and t equals 0. Putting in the deltas has made it much more general. Einstein makes an awful lot of sacrifices of clarity for brevity, it seems like for a tiny bit of extra ink. He could put in the delta for delta t and delta x prime and delta tau, or mention somewhere that this a variable that he's introduced is delta tau delta t. Okay, but now that I've gotten to the bottom of that, let's go back up to the paragraph I skipped. An analogous consideration applied to the axes of y and z, it being borne in mind that light is always propagated along these axes when viewed from the stationary system with a velocity square root of c squared minus v squared. Now this is referring to a thought experiment that involves at least 2 dimensions. So we kind of picture a particle, let's say a pair of particles moving along at a constant velocity. Is this a space? This is actually going to be a space versus space diagram with x going this way and y going this way. What we want to imagine is that at time t0, these 2 particles are here. At time t1, they are here, here, and here, and at time t2, they are here and here. At time t0, the lower particle releases a flash. At time t1, the second particle reflects it, and at time t2, the first particle receives the reflected flash. If the particles are moving along at velocity v, then this distance is v delta t, and so is this distance. And if the light is moving at the speed of light, then this distance is c delta t, and so is this distance. Now what we want to envision is a moving rod between those 2 things, between those 2 particles, and we kind of picture the ray of light moving alongside that moving rod, and I guess we could call the position of the photon along the rod y sub p, y photon, and the time in the stationary frame is t, as usual. So this is the t stationary, and we would have sort of a, how do they call this? Light is always propagated along these axes when viewed from the stationary system. So this would be c of c, I don't know, cy from stationary, cy stationary. Or maybe you'd call it c perp. C perp stationary. I don't know. I just need some kind of name for it so I can complete this triangle here and say that this side of the triangle is C perp delta t. So then we can just use the Pythagorean theorem and say that C perp is equal to the square root of c squared minus v squared. So this c perp is the velocity of light along an axis that is moving at constant velocity perpendicular to its length. So that was the easy part of this, the part we're all taking for granted, that just being borne in mind that light is always propagated along these perpendicular axes at square root of c squared minus v squared. Now we're left to our own devices and figuring out how an analogous consideration of these axes give us that del tau del y equals 0 and del tau del z equals 0. Now, given some time, I could probably find one or two, perhaps half a dozen reasons to say that the clocks in the y and z plane, in the yz plane, are synchronized when the object is moving in the x direction. The challenge here, though, is much more difficult because we're supposed to make an argument by analogy with what Einstein has already presented in this paper. So let's see whether we can come back to some equations he had a few lines before, the equations I hated so much because he uses x prime as both a coordinate and the length of a physical object. First, let me just fix it again and say x prime is the coordinate, so we won't use x primes in any of these locations. We'll just call that L for the length of the moving rod in the stationary coordinate system. So if we were to change this for, say, a length L along the y-axis, we're going to have tau of x prime equals 0, y equals 0. This is going to be where it starts, so this is still going to be 0, 0, 0 t plus tau of, it's going to be in the same position in the x prime system. It will have moved in the y system, or in the stationary system. And then this t, it will have come back to where it started in the y system. This t is going to be time plus, well, it'll be this delta t plus this delta t. And if this length is L, then that delta t is going to be L over c perp, which is square root of c squared minus v squared. So this time is going to be t plus 2L over square root of c squared minus v squared. And so that will equal this time, so half of the 2 is going to be the 1. And so this will be tau x prime still 0, but y will be L, z will be 0, and t will be just t plus L over square root of c squared minus v squared. Square root of c squared minus v squared. So now I'm trying to remember whether I actually found a way to get from this equation to this equation. My recollection seems to be that I did find a way to get some form of this equation, but it was more or less from scratch. Let me modify this equation, though, so that it actually has some of the same variables that I stuck in there. The L, namely. He has this nonsense about choosing x prime to be infinitesimally small, which just doesn't work if you've already decided that the length of the rod is x prime. That's just not how calculus works. But if I say that the length of the rod is L, then it is perfectly legitimate to take differential path elements in the space-time diagram with length partial x prime. But now I think I can see how to get the analogous considerations. Here, you see how our time of perception, t plus L over c minus v plus L over c plus v, minus our time of emission, t, yields this quantity, L over c minus v plus L over c plus v. And that is multiplied by partial tau partial t when x prime is held constant. We can do the same thing here. Take subtracting the time of emission, t, from the time of perception, t plus 2L over square root of c squared minus v squared, and multiplying that by partial tau partial t, where x prime is held constant. Now you see this term here, it was delta x prime equals L, but down here our delta x prime is 0 because the L is in the delta y, so that'll be 0 delta tau delta x prime. And here we have delta t, which in this case is going to be L over square root of c squared minus v squared. And we'll multiply that by partial tau partial t. Well, that is certainly going to give us an incorrect answer if we leave it at that. Well, no, not incorrect, more indeterminate. If I gather the partial tau partial t terms on the left, we'll find that when you subtract L over square root of c squared minus v squared from half of double the same thing, you get 0 del tau del t equals 0 del tau del x. Partial tau partial t partial tau partial x prime. Okay, so if we were wanting to get partial tau partial y equals 0, we need to try something else. Or maybe we could simply add a term to this expression here. We have delta x prime del tau del, or partial tau partial x prime, plus delta t partial tau partial t. What if we added delta y partial tau partial y? In this case, delta y would have been 0. Down here, we'll have delta y is L partial tau partial y, which gives us an extra term down here of L partial tau partial y, and down here L del partial tau partial y. Whoops, no, that's what we want. Anyway, this gives us, subtracting 0 from both sides, this basically gives us L partial tau partial y equals 0, hence del tau del y partial tau partial y equals 0. So I think the argument can be made that partial tau partial y is equal to 0, but it seems like this little paragraph here isn't so much an explanation as it is an exercise for the reader. And it's a sort of challenging exercise. And in the end, now that I've given an explanation for what I think he meant, I can't really prove based on what he says here, that he meant what I think he meant. That being said, my attitude toward this sort of thing is that if I can find an interpretation of the words that actually makes sense, that interpretation is generally unique. That is, I'm not going to find multiple valid but inconsistent interpretations. There will be just one truth, and small errors and lack of clarity in communicating that truth can be forgiven. On the other hand, I think that there are an awful lot of places in here where a lot of headache could be saved by providing diagrams, some additional explanations about the assumptions made, and a little bit more care taken in naming variables. So that's the service I'm trying to provide. Thanks for watching.